Okay. Thank you for the invitation. I am Swiss, and I am mathematician. I am not a specialist of pattern formation. I was involved in a project in systems biology in Switzerland, dealing with plant growth. So I had no idea of what is going on in plants. Now I know a little more, okay? And I will present you two basic models for auxin. Auxin is a plant hormone which is the main agent of pattern formation in plants. So I will first begin with well-known pictures. Okay, we see that in plants there are spirals, and so this is well-known. Turing was very interested in these patterns, and in fact he developed reaction diffusion basically when looking at phylotaxis, which is the arrangement of plant organs on plants. And so I know that everyone knows this, but if we count the number of spirals in a pine cone, for example, we find Fibonacci numbers, okay? And if we look, so in fact there is a basic spiral in the sunflower, and the spiral we see is different. They are called parastiche, but we can a basic model for the positioning of the seeds is that they are placed at a constant angle, okay? And it turns out that this angle is strongly related to the golden angle. So we see that in most of these patterns we have very regular geometrical structures. Like here, the leaves, if we count the angle between two consecutive leaves, we see again the golden angle, okay? More or less. So there are stochastic fluctuation, and a basic question is to understand how these patterns can emerge in real plants. First idea, very old idea of Meister. Meister was a biologist, and if we look at the center of a sunflower, for example here, this is called the meristem, and that's where new seeds are coming, emerging, and they move in this area, and he observed that the new seeds will choose the least crowded position. So they look for, in some sense, there is a repulsion force, and this repulsion force from the older primordia. So the new seeds will go at a position where it feels the least repulsion force. And we saw in many talks during this week repulsion potential and so on, okay? So this idea was already found by Hofmeister. And Turing was trying also to develop reaction diffusion models to explain phylotaxis, but for plant and for pattern formation in plant, it is not exactly what is needed. Perhaps for you who are specialists, you will see that the forthcoming models are in fact reaction diffusion models. For me it's different, but so using this idea of repulsion forces, a lot of new mathematicians and physicists developed mathematical models. So Adler used this idea. A physicist called Levitov is working in field theory and in statistical mechanics, and he used the repulsive potential to explain the positioning of the new primordia. Okay, like there is again based on this repulsion force, he came to number theory and found Fibonacci numbers and the golden angle. So we see that this basic principle of repulsion can explain the geometrical pattern we can find in plants. And next, Douadi and Kuder, they are two physicists, and they did an experiment. Okay. So here we have droplets, ferrofluid droplets. We fall into a pool of oil, I think silicone oil, and so each droplets repel each other, and they are attracted by the boundary. Okay. Here the frequency is very low, so the new incoming droplet is just filling the previous one. And so the direction where the force is, repulsion force is the weakest is in the opposite direction. In plants, this corresponds to the distic phyllotaxis, where the angle between leaves is 180 degrees. And this holds in plants where the plastochrome, the distance between leaves, is very big. Here the frequency is higher, so every new incoming droplet fill several of the previous droplets, and so the angle is not anymore 180 degrees. And so this is a well-known experiment I took on YouTube. So, and if we increase the speed, we will see spirals. Okay. So this is a practical experiment which mimics this repulsion potential. So now the speed is higher and higher, I think, and we see spirals emerging. Okay, so this shows experimentally that. Okay, I will stop. That such repulsion potential can explain phyllotaxis or lead to patterns. Kunz wrote a paper in Communication and Mathematical Physics modeling more mathematically than Levitov with rigorous mathematical arguments. A spin system in some sense with a repulsive potential, and he found relation with number theory, Fibonacci, golden angle, and so on. It's a very nice paper. And more recently, two mathematicians modeled this repulsion, this mechanism using dynamical systems, and they were again able to prove that the equilibria of the dynamical system are composed of spirals. Okay, but if we look at all of these models, they are based on a principle of repulsion. Okay, but from where is coming this? Is this repulsive force coming in biology? Okay, this is a basic question. And I will try to go more now in biology. So if we see a plant, the meristem it's at the top of the plant here, and new organs are coming, and this a very small piece of the plant. Okay, and in fact, the main agent for pattern formation in plants is auxin. So auxin is an hormone, a small molecule which is moving from cell to cell. So the auxin is traveling in the plant, and when it accumulates in some cells or in some set of cells, then it is a signal, so it attracts enzymes which modify the tissue. If I am an expert here, you can correct me, okay? But as soon as we have a high concentration of such molecules in some hot spot, they will modify the tissue, and I think, for me, with the pressure, I don't know, a new primordia emerge. Okay, so this is the basic. If we stop auxin in plants, nothing is growing, no pattern. Okay, so the presence or the accumulation of this molecule is absolutely necessary for pattern formation in plants. This is a biological. Here we have a picture of a meristem. In light green, we see high density hotspots of auxin, and that's where new primordia will emerge, new leaves, new seeds in sunflowers, and so on. Okay. So this is a fact, a biological fact. Here we see the movement of auxin molecules in the plant. So auxin is moving, accumulating in some hotspot, and after, during the second phase, the auxin must be evacuated from the hotspot because it is toxic. So the plants, as soon as there is a formation of a hotspot, a new primordia is emerging, a vein is being created to evacuate the auxin. So now, how can we model pattern formation in plants or auxin movement, molecules movements with the biological knowledge? Previously, all the above models used, as we have seen this morning, okay, or during this week, that there is a repulsive potential force, and now perhaps we look at the microscopic world and try to understand what is exactly going on in a plant. So the first model based on biology used the fact that meristem is viscoelastic, and so this Shipman and Newell, yes, in this last, okay, use von Karman equation to show that the patterns, for example, in sunflowers, are buckling phenomena. Okay? But again, we see this is not the main reason because auxin is not present in this model. But however, if we do the careful mathematical analysis, we can find they found exactly again Fibonacci spirals, golden angle, and so on. So we see that there is not a single approach to understand pattern formation. Repulsion, buckling, and biochemistry. So mechanics is strongly related to biochemistry. Okay, but up to now we didn't have any models dealing with biochemistry, that is with auxin flux. So two class of models appeared quite recently. Both models deals with the movement of these auxin molecules around in the plants. So auxin move from cell to cell, and they tried to model this movement, microscopic movement of auxin molecules. And a second, there is two families of models. So the first two models here are quite similar. Transition rate, if we think this at chemical reaction, are similar. But for the second class of model, the movement of auxin molecules are directly related to the flux. And for the two first models, the movement of the auxin molecules are based on concentration. And they look different, these two models. So actually there are two schools a little bit fighting, not really fighting, but they have completely different, not completely different, but quite different models to explain the same phenomenon. And last, Newell, Shipman, and Son used again the von Karman equation, but they plug the auxin transport model, so the model of Johnson, to model stress tensors in the von Karman equation. So they included the biochemistry in the stress tensor, okay, to see if it might help in understanding. Basically, auxin molecules are not, diffusion is very weak. The auxin molecule do not, I am a probabilist, so for me diffusion is a kind of random walk, okay? So auxin molecules do not move completely at random. If here we have two cells, they are transported by pin proteins. These proteins are transporters. They transport auxin, and they stay in a given cell. They don't move from cell to cell, but they can be either in the interior of the cell or in the interface, in the membrane, where they will help transporting auxin molecules. So, if we look at these two processes, now we have two agents. We have the auxin. Here we see hotspots of auxin molecules, so new primordia in a meristem. And we see here, for example, a primordium and the pin protein looking to the same cell because they transport many auxin molecules here. Okay, so there is a kind of polarization of the pin protein, so that auxin molecule can be transported at the same position. As soon as we have an auxin hotspot, around the hotspot there is no any more auxin molecules. We will see that this might explain the repulsion force in some sense, because when a new molecule, auxin molecule are coming, they will cross a zone where there is no auxin molecules, and so they will not have the tendency to go here. They will go in a different direction. But it's only an idea to have a repulsion from where this potential can come in biology. Here we see in a very I think it is a tomato embryo, and we look at two primordia. They are already positioned with almost golden angle. So this shows that quite soon geometry is coming. This is the second step I told you before. As soon as we have a new primordium, the auxin must be evacuated, and so the plant creates veins to evacuate the auxin. Now a mathematical model. I didn't invent these models, okay? So we have the cells. Ri is the auxin concentration. Pi is the number of of pin proteins contained in a given cell, I, and Pij is the number of pin protein located in the membrane facing from cell I facing cell J. Okay, so Pij is the number of pin protein located in this membrane. So the equation, the increase of the concentration of the auxin molecules in cell I is due to production term degradation, quite standard. In fact, in the meristem there is no production of auxin molecules. So basically, these two terms usually vanish here. There is no degradation. Here we have a standard diffusion term, okay, discrete, because I work with a discrete, I assume that the cells of the plants are disposed as a graph, any graph. So this is a Laplace operator in discrete form, and this means that both k and I are nearest neighbor in the graph. And we have the transport term. So T is a parameter to denote this active transport of auxin molecules by pin proteins. And here we see the increase of the number of auxin molecules in this cell is due to auxin molecules present in cell K moving to cell I. So we have the concentration here and the concentration of pin proteins at this interface. This gives this term here, and here the reverse term for molecules leaving cell I, okay? The second term, the increase of the concentration of pin protein at the interface AJ, is due to a feedback. This is a very important assumption. Here we have a standard degradation term. Here we have the So this means that the increase of the concentration of pin proteins in this membrane is proportional. You see here it is a linear function. So this is proportional to the concentration of auxin molecules present in this cell. This is like if pin proteins move to cell the neighboring cell when there is a high density of auxin molecules. I asked many times to biologists, how do pin proteins know that there are a lot of protein auxin molecules? They had some explanation, it's not known, but basically people think that the cytoskeleton is strongly related to the membrane, and a high density of auxin molecules will induce a signal here, but I have no idea.
In the neighboring cell?
Yeah. But so exactly how it can be realized in biology, I don't know. And so this is the reverse term, so pin protein can leave the interface, go back inside the cell, and it's the same rate, okay? Taking the adiabatic limit, that is, we assume that the equilibration inside of the pin, repartition of the pin protein inside the cell is very fast. To simplify the model, we get, and I deleted the first two terms, I get a model like this. And now the proportion of the transition rate, if you want, of the auxin molecules present in cell K to cell I is proportional to the hypothesis I just told you, the number of auxin molecules present in cell K, and divided by a constant plus the sum over all nearest neighbors of cell I of the concentration of auxin. So if this means that a pin protein can go in various interface, and will choose to go in a given interface K according with it's a weight which depends on the auxin concentration. It's just what I told you before. So here are some simulations. This model is able to lead to regular patterns. Okay? It's not what I obtained with simulation, and it's not what I obtained mathematically, because we computed all the possible equilibria and studied the stability of the equilibria of this dynamical system, which is quite strange. There is a continuous manifold of equilibria, and we didn't find such nice picture. So the second model. So the first model suppose that the insertion of pin proteins in the interface is strongly related with the concentration of auxin molecules in this cell. The second model assumes that does not involve the knowledge of the concentration here, but on the flux of particle crossing the boundary. This is the second model, is called the flux model. It's supposed to explain the same phenomenon. So the flux is just a diffusion term, okay, standard, and the transport term. It's called the flux. And the equation are like this. So the increase, okay, we see almost the same here, the diffusion and the active transport. But now the rate of insertion of the pin protein at the interface, so we have a basal creation term degradation, this is standard. But here we have a nonlinear function, phi, of the flux. And what is important, this nonlinear function is 0 when the flux is negative. So this means that there will be no pin insertion. I will come back. So there will be no pin insertion in this interface when the flux coming from here is larger than the flux outgoing from I. So as soon as a direction is favored with respect to another, then there will be no spin insertion. Okay, if this guy is negative, so this means that the ingoing flux is larger than the outgoing flux, then this term is 0. And of course, for the increase of the pin concentration Ji, it will be positive. Okay, so here are some simulation. So the colors are related to the auxin concentration, and with well-chosen boundary condition, we see very regular patterns. So at present time, nobody knows exactly which of these two models is a good one. If these models are, so all people I know in biology use these models. This is the basic models, okay? But which one is the good one? It's difficult to. I just present some since I am a mathematician, and I use techniques from probability theory to study this dynamical system. First, we looked for the equilibria, fixed point, so the dynamical system. So we put the derivative to 0 for people not involved in mathematics. So we get families of equation, of nonlinear equation, and we can rewrite the dynamical system like this. I assume here no diffusion to be simpler, and so this term I call this QKI. This is like in a Markov chain theory a transition probability, transition rate, and we can rewrite the equation f on A is 0, which takes this form here. You see it is linear in A, but the operator here, Q of A, depends also on A. And we can check that this is a Laplace operator. In some sense, this is a master equation for people, chemical master equation if you want. Okay? But for probabilists, this is Kolmogorov equation. And so we have a Laplace operator which depend on A. So we have, usually when we have, we look for a steady state, when we have a Laplace operator, this operator does not depend on A, okay? And the solution is a steady state. But here, we have the operator itself depends on A, so. But it turns out that if PA is the invariant measure of the Laplace operator, we must solve such an equation. And exactly a similar Markov transition Laplacian appeared in the theory of vertex reinforced random walks. Here it appears because, of course, the auxin molecules will move to a nearest neighbor according to the concentration of auxin in neighboring cells. So there is a kind of reinforcement in the auxin flux. So we use technique from vertex reinforced random walks to study the invariant measure. We found the solution, and we can prove the following. Let gamma be the adjacency matrix of the graph. Then A is an equilibrium if and only if gamma from A is a constant vector. And more generally, I assumed here what I said before, that all cells contained a positive number. The concentration of auxin was positive. But of course, if I look for general equilibria of this dynamical system, I can set to zero in black here the concentration of auxin molecules in some cells, and the concentration will be positive in the remaining cells. And so if gamma is a component, a subgraph here in red, I have for every subgraph such an equation to solve. This shows that you can have many possible equilibria to this dynamical system, and there is a continuum of equilibria. we look for the stability and look at the Jacobian matrix in terms of the adjacency matrix. It involves the product of the adjacency, the square of the adjacency matrix. Here we look techniques for Markov chain theory to study the linear stability, to check if the eigenvalues have a negative real part or not. And we found the following result. Here it is a subgraph, possible subgraph of the basic graph. If the diameter of this correspond to the, they were in red before, okay? I take subgraphs in a background of zero auxin concentration cells. So we proved that such a configuration is unstable when its diameter is larger than 2 on a grid, in a general graph. So for example, on a grid, if the cells are arranged like a grid, the only possible stable configuration are the subgraphs having a diameter less than 2. For example, these are unstable, these are unstable. And general equilibria are composed of building blocks which are such a subgraph of diameter smaller than 2 in a background of auxin depleted cells. And so this shows that the model people use is quite difficult, okay, mathematically. And we performed simulation, and we observed that during 1 week the system was approaching, for example, such a configuration, and we let 1 week wait, and so the configuration was completely different. So it seems that the dynamical system is approaching a manifold and then changing completely. So, but I will not have the time to discuss the second model. No, so I will stop here because if I have to speed. We did the complete mathematical analysis of the second model and obtained the stable configuration and so on. And so, just to finish, because I think it's at 3, I'm going to stop. I was too slow. Perhaps a simulation.
We have a little bit more time because we started like 3 minutes, 4 minutes.
I will just show. This is not a simulation of my. This is a simulation from the group in Bern who invented the first class of model. So they did a simulation on a growing plant. We see the meristem at the top, the pin protein and the interfaces, and we see the hotspot, so the new primordia. Here we have a phylotaxis. It is not a spiral, this is not a distinct phylotaxis. The angle, it looks like the primordia are opposed, okay? So by changing the parameter of the dynamical system, we can change the phylotaxis. You know, in nature we have several kinds of phylotaxis, okay? The distinct phylotaxis, where the angle is 180 degrees. There can be 2 leaves at the same, like cannabis. Cannabis, there are 3 leaves together appearing and after it's turning. So if you change the parameter, you can get all the known phylotaxis. Okay, but I think I will stop here. It's too long. I must go too fast to explain the second model.
Let's thank the speaker. We have time for questions. I have a question actually. I found it extremely interesting that you can show that these models, which so many people base their computational studies upon, that, for example, the uptake rate, where you compare the concentration in your neighboring cell, that in fact you only would predict certain segment lengths to be stable.
Yes, we look for the equilibria.
So my question is actually, why do you think that all these other simulations, which people are based, they say they base it on these principles, why do they seem to get bigger patterns or ranges? Do you have an idea, or?
I understood when I was working with this. They are very good guys, okay? But they tune the dynamical systems, they change the program. I have even seen people modifying the rate around the primordia so that the auxin cannot go any, But if you do the mathematics, you cannot. Mathematics are okay, You
so actually, just,
no.
It's just an observation. I have realized.
For me, I have an idea. I have an idea that primordia, these auxin configuration are only pre-patterns. They are not what biologists think the patterns. So we see that in plants there are regular patterns, but this. Okay. In nature it is like this. This looks like the equilibria I described, okay? Subgraphs in a sea of auxin depleted. But they are not, we see some regularities, okay? But I think they are pre-patterns. They are not the pattern we see in plants. But now with mechanics, perhaps with nonlinear elasticity, we know that when there is a high density of auxin molecules, it will change the nature of the tissue. Because enzyme will come, the auxin molecules are signals, so they attract enzymes, they will modify the tissue, and perhaps the turgor pressure, I don't no idea, okay? Yeah. And this should help the mechanics. On the other hand, biologists told me that mechanics influence biochemistry in plants. So tension, pressure, modify the way auxin molecules act and enzyme act. So, but I think it's impossible to predict regular patterns with this model of auxin, but to predict where pre-patterns are located, and next, the interaction with elasticity, I don't know, will position correctly the patterns. It's not really the buckling phenomena, but something we do not understand at present time.
How much data is there, experimental data, that one could...
all data is this kind of data. Auxin is extremely difficult to measure because it's impossible to observe auxin directly. They must put some agent, fluorescent agent in the auxin to see auxin. People think that auxin is concentration is very low. Some people think it is very high, some people very low. In some sense, auxin is a magic molecule which is very difficult to detect, but which is the main ingredient of plant growth. Everything which is growing in plants comes from auxin. There are several kinds of auxin, okay?
So I guess that's why it's difficult to rule out models. I mean,
exactly,
you have lots of models that give you very similar results, and one cannot quantitatively...
The second class of models do not lead to the same equilibria. They lead to vascular system. We did the analysis. We look for the equilibria. So a typical equilibrium of the second model leads to, these are cells which contain a basic, almost the same number of auxin molecules, a background. And in this background we have veins, which looks like oriented subgraphs. Because of this nonlinear function, as soon as one flux is positive, it must be negative, zero in this sense. Okay? So this has the effect to create oriented subgraphs. And here we see a sink, like a primordium here. A primordium corresponds to a tree pointing to a sink, a primordium. So I think that this model can explain, if it can explain the meristem and pattern formation in the meristem, this is for trees pointing to a sink. And I will go, this is a typical equilibrium. But here, if the primordium next is acting as a source, it evacuates auxin. So we prove that if there is a high density here is producing high density of auxin, then the graph is obligatory a linear tree. So this is a theorem we prove that the equilibrium is just a linear vein. Like in nature, they found in plants, it is a linear vein. So I think the second model is good for predicting the vascular system. And the first model is better to explain what is going on in the meristem. This is my point of view.
Okay.
I'm not sure.
So with that, I think we end the afternoon session. Let's thank all of the two speakers again.
Just one announcement.